All right, so 6.3 number 3a, use a common denominator approach to write this as a single term. So as I just mentioned, we have two terms here. There's one term, and here's a second term because it's separated by a plus sign. Over here, obviously, we have two terms. So we're going to try and combine those into one single term. This is a good strategy for proving identities, simplifying or manipulating sort of one expression. All right, so if I rewrote secant x, the second term, with a denominator of cosine, that's actually really easy because secant is 1 over cos, right? So 1 over cos x, is that correct? Cosecant goes with secant, or cosine, sorry. Cosine goes with secant, a co and a no co. So this actually would be simply sine x plus 1 all over cos x. You can't simplify it any further, but that's one single term. I think that's what they're looking for 3a. All right. The second one here might be a little more challenging, right? This is c. And to get a common denominator here, it looks like we're going to have to multiply both of these terms by the denominator in the other term. So, for example, I'm going to have to go, this is sine x over 1 plus cos x. And this is cos x over sine x. So, right now we see that to get a common denominator, it looks like I'm going to have to multiply top and bottom over here by sine x, because this term over here has a sine x in the denominator, this one does not. Also, this first term has a 1 plus cos x, which the second one does not. So I have to introduce that. And of course, what you do to the bottom, you have to do to the top, because in essence, you're not changing each term. You're trying to multiply each term by 1, or some form of 1, which sine x over sine x is 1. 1 plus cos x over 1 plus cos x is 1. But you're changing the way they look and express themselves. So this now becomes sine squared x, when you do sine x times sine x. And just another hint, this is really, really important. When you're getting a common denominator like this, try not to expand, multiply out these things. Leave them as separate factors, because factoring is really important to try to identify if there's something you can reduce with. So in this case, leave them as factors, don't multiply them in. Because if you have this big long polynomial on the bottom, and you're like, I wonder if I can simplify a factor out of there. Well, then you're just going to have to factor it again. So you're going to have to undo what you did. So leave factors alone in the denominator. That's a very good hint. Okay. This one over here is 1 or plus cos x plus cos squared x when you multiply this through, right? So I look at this and I actually, that's one single term, but certainly it looks like there can be some simplification. Do you guys see what sort of simplification I can do with this one big massive term here? Is there anything that jumps out at you that might be an identity that you could substitute something for? Sorry? Okay, sine squared x is something else. That's true. Yeah, so you could replace sine squared x with 1 minus cos squared x. You could. Excellent. You could also replace cos squared x with 1 minus sine squared x. You could do that. Or, to simplify things, to make your life just a little bit simpler yet, you could realize that sine squared x plus cos squared x equals what? Equals 1. That's right. So this actually could just go straight to 1 plus cos x over 1 plus cos x times sine x. And this is really the essence of proving identities. You're rewriting portions of expressions as identities, right? Rewriting them in a different way. And then now look what jumps out. You see what jumps out now? Now this is 1 plus cos x over 1 plus cos x. Those are common factors, top and bottom. I can get rid of them. So this is actually 1 over sine x, which is cosecant x. All right, so this is what we're going for here. Replacing this, like this whole thing right here. How many of you would have guessed that that just equals cosecant x, right? So a piece at a time, we replace, we simplify, and that's what we can boil it down to. Okay, any questions about number 3? Look good. All right, how'd you do with number 6? How'd you do with number 6? I'd love to go over number 6 with you here, just real briefly. So this number 6 says expand and simplify the expression of secant x minus tan x times sine x plus 1 to a primary trig function. So that's either sine, cos, or tan. So expand and simplify. That's another tool in the tool belt that we can do to simplify things. So when we do that, we're going to multiply. We're going to do FOIL method, really, right? So we're going to take this first term, we're going to multiply it into both those, and then take the second term and multiply it into both those. All right, let's see what we get here. So secant x times sine x. Well, here's a hint. Instead of writing secant x sine x, I mean, you could do that. And maybe we will do that. But in the future, you might want to say, hey, I know what secant x is. It's 1 over cos x. So 1 over cos x really is going to be multiplied by sine x here. So this might help. When you multiply this term times this term, if you rewrite things in terms of sine and cos, that might save you a step. All right? Now, don't go too many steps ahead and skip too many steps, because in your proof, you have to show all of the steps to get full credit for the proof. You can't just say, oh, I did 3 steps in my head and the left side equals the right side, I'm done. Right? That's the temptation, because you know the left side is supposed to equal the right side in your proofs. So you do have to show each step so that I can see that you're using the identities properly. But this is okay to do. 1 over cos times sine. Nice. Now we'll do secant times 1. Okay, well, again, let's go ahead and do a 1 over cos times 1. So 1 over cos x. Awesome. Let's do the second round of multiplication. Negative tan times sine. Well, that's going to be minus, what's tangent? What's another way to express tangent? Sine over cos. Okay, so this is sine x over cos x times sine x. Okay, that's a good thing. That's a good idea to do that. And then minus tan x, or minus, I'm going to say sine x over cos x. Now that looks really ugly. I get it. That looks very ugly. You're thinking, Mr. Maxwell, we're making things way more difficult than we need to. Well, I hope you're going to see that we're going to be able to simplify some of these individual terms. We're going to be able to, we have some like terms. For example, sine x over cos x, I see here. This is sine x over cos x, and guess what? This is sine x over cos x. And actually one is positive and one is negative. So do you see how those just cancel each other out? That's actually kind of nice. You can go show your work just like this. Say, hey, I have sine x over cos x. They're going to cancel each other out. Okay. So 1 over cos x, let's rewrite that. 1 over cos x. And when we simplify this one, what do we get? Sine squared x over cos x. You see, sine times sine over cos. All right. Okay. What jumps out at you now when you look at that expression there? What jumps out at you? Should be a couple things that jump out at you. What do you see? Tell me.
Common denominator.
Common denominator. Very good. We could smash those things together, write it as in terms of one term. That's beautiful. Anything else you see? Okay, you see a 1 minus sine squared there. Yeah, you see a 1 minus sine squared. Now, when we combine this into one term, because it has a common denominator, we will have 1 minus sine squared on top. And that is something that should pique your remembrance too. Exactly. The other thing you might say is, hey, sine squared I know equals 1 minus cos squared. So that also might jump out at you. But those are great. So let's continue down that vein. I'm going to combine these together. Whoops. 1 minus, come now. Computer. There we go. 1 minus sine squared x over cos x. That's what happens when I combine these two terms together. And the 1 minus sine squared was mentioned. That actually is the same as cos squared, isn't it? So now I have cos squared x over cos x. And we wouldn't have to write this out, but you understand that cos squared x is the same as cos x times cos x, right? And so one of those will go with one of those. You can, this is what I do, 1 cos goes with 1 cos, and I just stroke out the exponent too. And so you can, that shows me that you know what's going on. And finally, this just boils down to a simple cos x. So if someone wants to double check the solution there. I don't know if they give a solution, but it should be cos x, what this should equal. If I have done everything correctly here. So what do you guys think? That make sense?
Yes.
If you look at that whole thing and you're like, wow, that's a mess. Yeah, one step at a time though is not so bad, right? One step at a time is not so bad. Okay. Okay, I have, let's see, from your assignment, MrMathWell.com here, you're looking 1, 2, 3, 6, 7, 11. Okay, do we want to take a look at 7 or 11 for any of you? Or were there any other questions from your assignment that you'd like me to go over? Because I have a bunch of things here that I could do. Any questions jump out at you that you're looking at?
11A.
11A? Oh, okay. Is that? All right. Okay, let's take a look at 11A. So here we go. We are actually proving the identity, and this is exactly what this is the crux of the situation here. This is the most important part. This is what you're trying to do from beginning to end. So I'll just try and find a spot here. Do I have a spot? I got so much work from other years here. Okay. That's 9. Okay, well let's do 11 down here. Okay. All right. So now, which is the more complicated side? Like, which has more to work with? The right side or the left side? Yeah, the left side, right? We got double angles. We've got adding different terms. We got all sorts of things that we can do here. That we can replace things. We can get common denominator and add. Okay, so we're going to work on the left side. Again, that's the strategy that I suggest. Is that you pick one side and you work almost entirely on that one side would be best. So I'm going to put cosecant x over here, and I'm going to work on this left side to try and replace things. So I see a sine of 2x there, and I see a cos of 2x. So I'm wondering if we can replace sine of 2x with one of its double angle identities. So let's see. Do I have something right here? This right here. The double angle identities, sine of 2a is 2 sine a cos a. Okay. Okay, well I think I like that. Let's try that. So 2 sine x cos x would be from that identity. So sine of 2x is the same up here as sine of 2a. So that's 2 sine x cos x. Everybody see that? Now, why did I like that? Why do I like that a lot? Because of what? Nice, you got a cos x on the top and one on the bottom now. That's going to be real handy, right? Okay, we're going to be able to simplify this, reduce this a bit. Now, what about the cos of 2x? Remember, I have a sine x on the bottom. Let me just grab this and copy it and bring it over. Yeah. Let me try and plop that right there. Come on. There you go. Okay. Okay, that's a little small for you guys to read, I get it, but let's see. So cos of 2, now we have options with cos of 2x, that seems, and I have a sine x in the denominator, so, well, I could do cos squared x minus sine squared x, perhaps. I could do 1 minus 2 sine squared x. The cos one, I don't know. Probably stay away from the cos one just because I've got a sine already in this. So what do you guys think? Which one should we choose to replace here? There might be one that makes things a little simpler 2 or 3 steps down the road, but you don't know that a lot of times. So we could probably pick either one. Which one do you like? Do you want the 1 minus 2 sine squared a, or do you want the cos squared minus sine squared 1? The 1 minus, okay, I heard a couple people say 1 minus. Let's do that one. 1 minus 2 sine squared x. Okay, sine x. Okay, I like the 2 signs there. I cannot cancel these out because these signs, the sign on top and bottom, are not factors. There's a big fat minus sign here so that they are not multiplied together. So you can't do this, guys, okay? Don't do that. That is not mathematically acceptable, okay? Because it's only factors that you can divide out, right, to be 1. So, go away. Not responding. How can you tell it's Monday morning? My computer is... Okay. Come on, computer. All right, there we go. Okay. All right. So I'm going to get rid of the cos here. So that cos is going to go bye-bye. Cos and cos is gone. Okay. I'm going to, anything else I can do? Well, let's rewrite and see what happens. So 2 sine x plus 1 minus 2 sine squared x. Now, we don't have a common denominator here anymore, do we? Okay, so I have to write this here. Okay. All right. Thoughts? What do you see? What? Because we're not done yet, right? We got to get it to cosecant x. We're gonna have to maybe put those two together. Might be a good idea. Because there's no real simplification I can do for each separate term. So should we try and do this addition? Yeah, I think so. Let's get a common denominator, which is kind of handy because if I multiply top and bottom by sine x, look at what I get. I get 2 sine squared x on top because 2 sine x times sine x is 2 sine squared x. And that should excite you in a mathematical sort of way because I have positive 2 sine squared and I have minus 2 sine squared with a common denominator. So guess what? We're going to be able to do some pretty fancy stuff here. So we're going to end up with just a 1 over my common denominator of sine x. Ha 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 ha. And now I'm really excited. Now I am super, super excited because now I can see that just rewriting 1 over sine x as cosecant x gets me the exact same term as I have on the other side. And we haven't brought anything from one side to the left side. We haven't done any equality sort of characteristics there. And I've shown the left side is actually equal to the right side, just using identities and mathematical operations within that side. So I am done. QED, quaderat demonstrandum, that which was to have been demonstrated. Done the proof. Okay, everybody like that? Everybody okay with that? Is anyone else as excited as me about that?
Me.
Okay, one, good. Anybody else? No, just one? Okay, all right. Well, thank you for containing your excitement there. You're doing very well at that. You're disciplined, okay? All right. Okay, any other questions you have for me about your assignment that I've given? So if we take a look at B and C to finish off this, cosecant squared, secant squared, there are some Pythagorean identities you can replace here. I don't know which side you want to focus on. Doesn't really matter. You could probably rewrite both this term and this term as two different identities and then see if you can cancel anything out, see if there's anything you can do. Over here, if you focus on the left side, this one right here might be a little on the tricky side because these are close to identities right here, like cotan x minus 1 and 1 minus tan x. Those are close, but they are not identities, are they? Because we need squareds in there. So guess what? What you can do is multiply top and bottom of the left side here. You can multiply the top and bottom by 1 plus tan squared x if you want to get a difference of squares. Then you'll be able to switch something on the bottom. Or cotan x plus 1 multiplied by the conjugate. So I don't think we've done an example like the conjugate. Have we done that example for you guys this year? Okay. So sometimes, and maybe we'll take a look at 11C here. May as well. Anyone done 11C? Has anyone finished 11C? Okay, maybe one hand. All right, well, let's do 11C together. There we go. Okay. Let's bring this down so you can see that if we need to. Okay, so I would focus on the left side here. It's a little more complicated. Again, to expand to try and get this from simpler terms, not as easy as taking more complicated stuff and trying to boil that down. So yeah, like I said, let's see if we can see. It's not on here. Sorry, give me 1 second here. So with the Pythagorean identities that you see kind of down here in this area here, I see 1 plus tan squared equals something. That equals secant squared. Okay, well, 1 plus tan, if I could get 1 plus tan squared, that would be great. I get equal to secant squared. 1 plus tan squared might be tricky though, because I'm going to end up with a difference of squares if I multiply by the conjugate. So that's going to be 1 minus tan squared. 1 minus tan squared. So that's a bit, maybe that might not be as friendly. What about the cotan? If I multiply by the conjugate, that is cotan x plus 1, I'm going to get a difference of squares. That's going to be cotan squared x minus 1. Do I see that anywhere? Cotan squared x minus 1. Oh, man. Okay, well, it's, okay. Nothing looks directly friendly. Like I can't see, 2 or 3 steps down the road here. So I don't know. Let's try something. Let's do the conjugate method here, where I'm going to multiply top and bottom by. I'm going to go 1 plus tan squared x. Okay, so top and bottom by 1 plus tan squared x. Let's just see what happens when I do that. So I have cotan x minus 1 on top times 1 plus tan squared x. Oh, cotan and tan, that's interesting. I'm sorry, not tan squared, just tan x, not squared, sorry, not squared. So tan times cotan, that's going to be pretty interesting up top. I like that. That's going to be interesting, because cotan and tan, when you multiply them, should equal 1, right? Because they're reciprocals of each other. And then, of course, down the bottom here, when we multiply this, that's going to be a difference of squares, because it's the same term with same two terms, opposite signs. So when I do my FOIL, I'm going to end up with 1 minus tan squared x. Okay. All right. Okay. No direct identity for the bottom one, doesn't look like. But I'm really intrigued by this top one. I'm going to multiply this top. I'm going to do the FOIL method there. So I'm going to have cotan x. And then I'm going to have cotan times tan is 1. That's going to be awesome. And then I'm going to do minus 1. Hey, nice. I'm going to do this one. And then minus tan x. Okay. Okay. Over 1 minus tan squared x. Okay. Well, the ones I can get rid of. That's nice. That's nice and handy. One I can get rid of. Cotan x minus tan x. Those are real close, but let's see. I can't really combine those together yet, but I wonder if I should rewrite cotan as either 1 over tan or cos over sine. Now, 1 over tan seems to be pretty reasonable, so watch this. I'm going to go 1 over tan x minus tan x all over 1 minus tan squared x. All right, so this is a real big kid problem here. Okay, this is not easy. You guys are doing great here to keep track of this. So again, but it's one step at a time, and whatever you can see, you do. So now I'm seeing that I should probably perform the indicated operation, and by doing that, watch what's going to happen. I'm going to put a common denominator of tan x down here, which means I have to multiply the top by tan x. Well, that's going to be intriguing, because now I have 1 minus tan squared x. You see that? 1 minus tan squared x all over tan x all over 1 minus tan squared x. Weird, eh? Not weird? Okay. Now, when you get to this point, you've got divided by divided by. Most of you should know at this point, when you divide by two different things twice, like when you divide and then you divide again, it's the same as taking this bottom one and flipping and multiplying, right? Remember that rule? You flip and multiply a fraction that you're dividing by. Okay. Or another way to think about this is, it turns out to be that you have this on top, and then you have these two as products on a single denominator. That's the way it turns out. So it would be, it's going to end up to be like this. I'll try and change colors here. It's going to be 1 minus tan squared x over, you flip and multiply, you're going to get tan x times 1 minus tan squared x. Now this is looking beautiful. This is looking really, really encouraging, because now I have a common factor on the top and a factor which is multiplied on the bottom. And guess what? Those go. They're gone. I'm left with 1 over tan x. And if I go back and look at what I'm actually aiming for, I'm aiming for cosecant x over secant x. Okay. Cosecant x over secant x. So here's where you might want to start to work on both sides a little bit, okay? Because it might help out here. Cosecant x over secant x. Cosecant x over secant x. So let's try and figure this out. Well, it might be a good idea to write everything in terms of sine and cos now. So this is 1 over tan x is actually 1 over sine x over cos x, which is cos x over sine x. And you can see that kind of here and here. That 1 over tan x actually is cos x, which is cos x over sine x. You see that? So using identities, and this is an acceptable one step skip. That's an acceptable one step skip there. And over here I have 1 over sine x divided by 1 over cos x. And of course, when you flip and multiply, you get cos x over sine x. And there you go. You've actually got them both to be equal, the exact same thing. So that is just one way of showing that proof. And honestly, there could have been several other ways that we could have attacked that by doing different things earlier on. But that's an example of one of the proofs that you will get on your hand-in assignment that I'm going to give you shortly. Okay? So this is one of the tougher ones. This is what some of your questions will be like. You have to do on your own. So any questions about that? Okay? You can do it. You can do it. It's maybe a little daunting at first, but use the tips that I gave you in class the other day and just do one step at a time. Yes? QED, remember that's the Latin for quod erat demonstrandum, which means it has been demonstrated. That which was to have been demonstrated is complete. So I just suggest you put that at the end of your proof to signify that you're done. Because really, there is no solution, right? There's just a proof. So it's like I've concluded my argument. And you would have something like this. Your left side of your work equals the right side. And you're just stating that your argument is now complete. All right. Anybody else? Any questions?